Welcome all to the third lecture of Mechanical Engineering Materials. Our today's topic is crystal structure, unit cell and space lattice. Let's start with the unit outcome that we will study during this lecture. As we know, unit outcome helps us to understand the outline of the unit. In other words, unit outcome is something that we will be studying in this unit. As you can see, we will go through the highlighted first three highlighted unit outcome that are: the first one is to interpret crystal structure of given material, second is to interpret structure of specified materials at a given level, and finally we will try to understand the microstructure of given material with justification. Now let's move on to topic level outcomes. Topic level outcomes, or TLO, are just like our unit outcomes, but these are focused mainly on the current lecture. In this lecture, we will cover the topic outcomes as follows. First is crystal structure, second is unit cell, and third one is types of crystal structures. Let's start with the first topic, that is crystal structure. Structure means geometric relationship of material components. Structure means the arrangement of internal components of matter or atoms. The arrangement of multiple unit cells together is called as a crystal structure. Crystal structure is an example of atoms in a different pattern. Let's understand this with an example of brick house. In this case, each brick acts as a building block or unit cell of a house. Just like in this case, this crystal structure, the red and green spheres represent various atoms of the material. Now let's discuss what exactly unit cell is. So the unit cell is the smallest representation of geometry of a crystal structure. The smallest repeating unit in a space lattice, which is when repeated over and over again results in a crystal of a given substance, that is called as a unit cell. This is the unit cell that we will be studying, a cubic unit cell. It has 8 sides or 8 vertices with atoms at each of its 8 corners and having 6 faces or 6 planes. This unit cell is when repeated multiple times we get a crystal lattice or crystal structure. So unit cell, you can say, is simply a box with an atom at each corner. We can understand the basic structure of unit cell from these figures. Multiple unit cells connected combine to form a crystal lattice. Next topic of discussion is space lattice. A space lattice is an array of points showing how particles, that is atom, molecules, ions, are arranged at a different sites in a three-dimensional space. This is your three-dimensional space which represent your x-axis, y-axis and z-axis. So as you can see, unit cell is nothing but representation of atoms, molecules or ions in the three-dimensional space, showing a space lattice or crystal structure. This is an example of simple cubic crystal which has 8 atoms at its 8 corner. Now the constant distance between the adjacent atom, these two are adjacent atoms, similarly these two, this distance between these two adjacent atoms is called as lattice constant. Let's understand it with a practical example. A space lattice can be considered as an apartment building. Here each flat represent a unit cell, and with these multiple flats available in apartment society, that apartment society is nothing but your space lattice. So as discussed, multiple unit cell leads to formation of a space lattice. Now after understanding these concepts of crystal structure, space lattice and unit cell, let's go through different types of crystal structure. First we will understand this simple cubic crystal structure or simple cubic crystal. As discussed, a cube has 8 sides or 8 corners, and each corner has a atom at its place. Then that type of a cubic crystal is called as a simple cubic crystal. Okay. Now let's move on to the complex types, that is cubic body center or body center, that is BCC, cubic face center, that is FCC, and finally hexagonal close pack structure or HCC. Now let's do a comparison study of these three types so that we can understand it in details. So this is the comparison study, and the parameters that we are considering for the comparison are number of corner atoms, number of center atoms or face center atoms, coordination number, packing factor, and examples. So as we can see, the body center cubic structure, that is BCC, has 8 corner atoms. Here 1, 2, 3, 4, 5, 6, 7 and 8. One center atom, as we can see this atom which is the center atom. Coordination number is 8 and packing factor is 0.52. We will discuss these two concepts in next slide. As of now, just remember the numbers. Like for PCC, the coordination number is 8 and packing factor is 0.52. You will definitely get an easy type of question, a 1 mark type of question on these topics. Like you will ask what is the coordination of BCC and you will be given 4 options. So all you have to do is remember the number. You will not be asked to explain what coordination number is or what packing factor is. You just have to remember the numbers. Similarly, now let's understand the examples. The examples are lithium, sodium, potassium, chromium, barium, vanadium, alpharium and tungsten. Similarly, let's look at FCC, that is face center cubic structure. Here also we'll see there are 8 corner atoms, 1, 2, 3, 4, 5, 6, 7, 8. You can see it from the figure. Similarly, it has 6 face center atoms. So unlike BCC, here there is no atom present in the center of the cube, but 6 atoms are present in the center of each face of the cubic. A cube has 6 faces, that is 6 plane, 1, 2, 3, 4, 5 and 6. So 6 plane and each plane has a center atom. So it has 6 center atoms. Here the coordination number is 12 and packing factor is 0.68. The examples are copper, silver, gold, aluminum, nickel, platinum and lead. Now finally, let's look at hexagonal close pack structure or HCC. Here you can see the hexagon has 12 corner points, 6 at top and 6 at bottom. So in total it has 12 corner atoms. In case of center atoms or face center atom, it has only 2 center atoms. One is in the upper face and other is in the bottom face. Similarly, the coordination number is 12 here and packing factor is 0.74. You can see the packing factor of hexagonal closed pack structure, that is HCC, is greater than FCC as well as BCC. And the example of HCC are beryllium, cadmium, magnesium, titanium, zinc and zirconium. Now let's understand what exactly the coordination number and packing factor is. So coordination number, which is also called as a ligand C, is the number of atoms, ions or molecules that a central atom or ion holds as its nearest neighbor in a complex or coordination compound of or in a crystal. Now let's consider this atom present or rather shown by a red dot or red color. This atom is common with 8 unit cell. You can see they are represented by different colors: yellow, brown, green, purple, blue, etc. So these color represent 8 different unit cell, and this atom is common with these 8 unit cells. So coordination number is nothing but the number of times an atom is shared with different unit cells. In this case, this atom is shared with 8 unit cells, so the coordination number is 8. This can be considered as example of BCC or a simple cubic structure. So as we have seen, the coordination number of BCC is 8, and which we can be understood by using this example. Here the atom is shared by 8 unit cells. That's why the coordination number is 8. Now let's look at packing factor. So packing factor is nothing but the volume ratio of volume of atoms to the total volume of cell. So what exactly volume of atoms means? The number of atoms into the volume of atoms. So number of atoms, for example, in a BCC, the number of atoms that we have to calculate, there is 8 corner atoms and 1 center atom. So that is 9 into volume of atoms. So each atom is considered as a sphere, and for sphere the formula of volume is 4 by 3 pi r cube, where r is the radius of sphere, divided by volume of unit cell. As we have discussed, the unit cell for us is a simple cube, or a cubic structure, and for a cube the volume is the cube of its sides. So using this formula we can calculate the packing factor of any type of a crystal structure. Now let's go through some practice questions. First is, crystal structure is arrangement of dash in a different patterns. The options are electron, protons, atoms and crystals. So let's look at the slide where we have discussed the crystal structure. Here we can understand crystal structure is an arrangement of atoms in a different pattern. So here the answer is C, that is atoms. Next question, smallest representation of geometry of crystal structure of a material is called. Options are lattice, crystal lattice, unit cell, crystal structure or crystal. We know that crystal lattice is made up of various number of unit cell. Crystal structure, it is also a type of crystal lattice and different name for crystal lattice, and it is also made up of a unit cell. So here the answer must be unit cell, which is the smallest representation of geometry. We have seen an example of a brick house where the brick is the unit cell for preparing the whole house. We can confer it from this side. The smallest representation of geometry of crystal structure of a material is called as a unit cell. Let's look at question number 3. In a simple cubic structure, there are dash number of center atoms. We know the simple cubic structure has 8 corner atoms, but let's see if it has any center atoms present in it. Here this is an example, or this is a representation of simple cubic crystal. As you can see, it only has 8 corner atoms but no center atom. So here the answer is D, that is 0. Now let's look at the final question. The packing factor of body center cubic structure, that is BCC, is, options are 0.42, 0.52, 0.68 and 0.74. So we can get the answer from our comparison slide where we compared these type BCC, FCC and HCC. So let's go through it. So as we know, the packing factor of BCC is 0.52. So here the answer is B, that is 0.52. Okay, thank you. I hope you guys have understood all the concept that we have discussed in the lecture. In next lecture, we'll discuss a small concept, that is the sample preparation and etching process. And if you have any doubt, please let me know so that we can discuss that in our coming lecture. Thank you.